We've now covered two types of nucleophilic substitution. The straightforward one where you're doing it with hydroxide or cyanide, and the slightly trickier version where you're doing it with ammonia, where there's a second step where another ammonia comes in and acts like a base and deprotonates the NH3 plus group to turn it into an amine. We can go further than that. And it's not a new mechanism that we're going to introduce. It's not even a more complicated mechanism. It just looks more complicated. There's no point trying to move on to this mechanism until you are really confident and happy with nucleophilic substitution with ammonia. Now, one of the conditions for this was excess ammonia, and that means we're going to have this reaction happening a lot. Let's say we don't have quite so much ammonia, that we still get this reaction happening, but if we look at what we produced, we've got this ethylamine, or ethylamine. I'm not quite entirely sure how to pronounce it. Now that could also act as a nucleophile. And if that can act as a nucleophile, it can attack the bromoethane. And we're going to have a look at what happens then. So let's get rid of everything else. Yeah, almost got rid of everything else. One day I'll learn how to use a computer. And we're going to react this one with ethylamine. So CH3, CH2, NH2. We're going to see what we produce. So let's draw it out. So we've got our bromoethane. We'll pop on our partial charges. Delta minus on the bromide, delta plus on the carbon. Now we're going to draw out our ethylamine. And I'm going to draw this one the opposite way around to how it's written up there. Now I'm doing everything here displayed, which actually makes it look really messy, but it's probably the most fundamental way for you to see what happens. Now, this nitrogen on the ethylamine, if you think about what I said when I first introduced amines, really they're just ammonia where you've replaced the hydrogen with a carbon chain. What didn't change at all was the fact there's a lone pair on that nitrogen. So we've got something here with a lone pair that I said was based off ammonia. So if it's based off ammonia, it can do exactly the same thing that ammonia will do. It will act like a nucleophile, and that lone pair will be attracted to the delta plus carbon in the polar bond, and then the carbon bromine bond will break. So now let's see what we've got. And also let's quickly just change the title, because we're no longer doing this with ammonia, we're doing it with an amine. And you'll do a lot more of this in your second year when you study amines. So really, that amine is the same as ammonia, except one of the hydrogens has been replaced by a carbon chain. So it will do the reaction in exactly the same way. So let's draw our product. The bromine has been replaced by the nitrogen. The nitrogen has two hydrogens coming off of it, and then a two long carbon chain. So this is now what we produced. But don't forget, there's a plus charge on that nitrogen. It's got too many bonds, so it's got a plus charge. So what can happen now is our ethylamine, again, can act just like the ammonia did. It can act like a base. So rather than drawing the whole thing out, I'm just going to abbreviate it to that. And when it acts like a base, the lone pair on the nitrogen, so I've not really put in the most useful position there, but hey ho, that's going to deprotonate the nitrogen, so it's going to take away the hydrogen, and then the nitrogen-hydrogen bond, the electrons from that are going to move to the nitrogen. What we're going to end up with here is CH3, CH2, NH. That will be NH2. It's just going to be NH, sorry. And let's actually draw that hydrogen on there. CH2, CH3. So now we have diethyl amine. So the amine is just a more complicated looking version of ammonia, really. But it reacts in exactly the same way. So in this equation, we should actually have two of them. And we've formed CH3, CH2, NH, CH2, CH3. And this time the salt is CH3, CH2, NH3Br. Now, it would be nice if it stopped here, but obviously it's not going to, is it? Let's be honest. We can react this further. Now, we've got our ethyl or diethyl amine. So let's draw this one out in full. And I'm going to show you a little cheat, which isn't really a cheat. It's an absolutely essential part of organic chemistry. But drawing out all of these carbon chains, let's not forget there's a lone pair on that nitrogen, gets a bit tiresome and a little bit annoying. So we can actually then just say that carbon chain, we're just going to call it R. And the other carbon chain, we're going to call R prime, R dash, whatever you want to call it. The fact that they're the same, we could just call them both R, but this is what we're going to call them for now. So that chemical we can actually just write as R like that. So what can happen next is let's go back to our ethyl bromoethane. Pop on our partial charges, and hopefully you can actually guess what's going to happen now. That should be a hydrogen, sorry. So this diethylamine, which I'm now just drawing as this, still got a lone pair on the nitrogen. It can still act as a nucleophile. It can still attack that carbon. The carbon halogen bond will break. Now we're going to end up with the CH3CH2 N, got an R group, got the other R group, and a hydrogen. It's going to have a plus charge on the nitrogen. So now what will happen, if a second one of these comes along, which is absolutely fine to do, it's going to, so I'll put this at a weird angle, but the first one acts as a nucleophile. Second one, again, is going to act as a base in exactly the same way that ammonia does. So it's going to take that hydrogen away, and then the nitrogen-hydrogen bond is going to break. And what we produce this time is a nitrogen with 3 R groups on it, and we're just going to call this other one R prime. And it's still got a lone pair. So this is how you can start with ammonia, and you can just keep putting more and more carbon chains onto it. But why stop there? Let's go back to our bromoethane. This time we've got our nitrogen with 3 different R groups attached to it, and therefore we call this one a tertiary amine. We've still got the partial charges on the halogenoalkane. This first step, it's still going to act as a nucleophile. So it's still going to attack the carbon halogen bond is going to break. This time, what have we got? We've got a nitrogen. We've got the CH3CH2 group that we've got from this one. We've got, you know what, let's write this one all out. The CH2, CH3 group from the first substitution. The CH2, CH3 group from the second substitution. The CH2, CH3 group from the fourth substitution. The nitrogen still has a positive charge. We call this one, when it had 3, we called it tertiary. This time we're going to call it a quaternary salt. So it's quaternary because it's now got 4 things attached to it. Now we have the tertiary amine, which has its lone pair. It wants to act as a base. However, what does a base want? It wants to accept a hydrogen. It can't touch the hydrogen bonded to the carbons. They're nice and safe with the carbons. It wants to get one of the hydrogens attached to the nitrogen. But look what happens. It can't. Because there's no H on the nitrogen. So therefore, when you get to this step of the further substitutions, you cannot do the second step. It can't act as a base. And actually what it is going to do now, that bromine, which came off in this first nucleophilic substitution step, it's going to form this quaternary salt. Now, if you don't get that, that's absolutely fine. We'll cover it again when we do amines in the second year, but it linked quite nicely into nucleophilic substitution now, and there's a good chance by the time we do it next year, you'll have forgotten nucleophilic substitution. And that is nucleophilic substitution with an amine.